following video is on the fundamental theorem of calculus, parts 1 and 2. For the warm-up, find the derivatives of each function below. Hopefully you found the derivative of each function below. F prime for f1 is 3x squared. f2 prime is 3x squared. And f3 prime is 3x squared. So what you notice is that all three of these functions had the exact same derivative, even though they're different functions. And we can show that is true using everybody's favorite thing, which is Desmos. So it doesn't really matter what I make x cubed plus some constant, my derivative is always 3x squared. So it doesn't really matter what the constant is in that case. So we're going to define what an antiderivative is. So a function f, capital F, is an antiderivative of f on an interval I if big F prime is equal to little f for all x in that interval. Okay, so a couple of things that are important in terms of definitions. Notice we say an antiderivative. The reason we say that is because there are technically infinitely many antiderivatives of any function. So if we have a function lowercase f, basically what we have here is all of these we would call lowercase f. So like we could replace big F prime with little f for all of these cases. So f1, f2, f3, we could have a bunch of different f's, all that have different c's. They would all still have the same they would all still have the same derivative, okay? So the derivative we call little f in this case. Capital F is what we call the antiderivative. So they have a relationship where if we take the derivative of f, that's equal to this little f. So what we end up noticing is that all of these little f's are the same, even if these big f's have different constants. So the function f is an antiderivative of this little f if big F prime is equal to little f. Therefore, when we are taking an integral, which is often associated with antiderivative, so when we take an integral, or an indefinite integral especially, that's when we have an integral here that doesn't have any numbers that are associated with it. So if we just take the general integral or the indefinite integral of x squared dx, we get 1/3 x cubed plus c. So the c is a constant. It could be any value. We don't know what the value is most often. Now, there are some problems where you're going to have to solve for c. Those problems, when you're given some condition, so for example, if you're given some point that's true on the original function, you can find c. But if you're not given some point, then we would just keep c as plus c. Okay, so then that leads us into the next thing, the fundamental theorem of calculus, part 1. There are two parts to the fundamental theorem of calculus. We're going to talk about part 1. If f is continuous on the interval a to b, then the function capital F is equal to the integral from a to x of f of t dt, has a derivative at every point, and we know that the derivative of this integral ends up being the original function that we took the integral of. So just as an example, the integral from 4 to x of t squared dt, that's basically the same as this problem up here. But we have to use what's called a dummy variable or a placeholder variable because we can't take the integral of something and sub in the exact same variable. So if I do this, what I end up with is some sort of integral like 1/3 x cubed plus c. Now, when we do the fundamental theorem of calculus part 2, we'll end up figuring out exactly what's happening to this thing, and we'll figure out like how we can sub these things in. But basically what we end up with here is something like 1/3 x cubed, and then there's a plus c. Now we would find out that in this particular problem, that plus c ends up being 64/3, or negative 64/3. But in any case, it doesn't really matter. What we do want to know is what happens when we take the derivative with respect to x of this integral. So I found the integral. Now if I take the derivative with respect to x of this integral, what I end up with is the derivative of 1/3 x cubed, which is x squared, and the derivative of any constant is 0. So what I end up with is I end up with the exact same thing that I started with. So notice that if I take the derivative of the integral, I get the original function. That is very, 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 very important. That is something that will help you remember what is actually going on. The fundamental theorem of calculus is basically the derivative of the integral is the original function. The derivative of the integral is the original function. Okay, so now that we know that, let's do a bunch of examples. A couple examples with antiderivatives. So if we're finding all possible antiderivatives, remember we have to put a plus c at the end. That is super important. If it's asking you for an indefinite integral or an antiderivative, you should probably put plus c at the end. So in this problem, the antiderivative of 2x squared minus 4x plus 17, the antiderivative of 2x squared would be 2/3 x cubed. That's because if I took the derivative of 2/3 x cubed, I would end up with 2x squared again. Minus 2x squared, because if I take the derivative of minus 4x, or if I take the derivative of negative 2x squared, I would end up with negative 4x. And then plus 17x plus c. So notice each part of this f of x that I have here, if I take this antiderivative, if I take the derivative of each part of this, I'd end up with what I started with, and notice the derivative of c is going to be 0. Number 2, an antiderivative of cosine of x is sine of x, and then we have plus c, because we don't know exactly what it is. F prime being 5 over x, my f of x will end up being 5 times the natural log of the absolute value of x. One thing that is important when you're taking the antiderivative of natural log or of 1 over x is you put an absolute value bar, but we'll learn that next chapter. So I just kind of want you to be aware, though, that if we see 1 over x, that was the derivative of natural log of x. So that means if we want to find an antiderivative of 1 over x, we have to go backwards and see that it's natural log of x. Okay, a couple things. Fundamental theorem of calculus. So if we take the derivative of the integral, we end up with the original function. Now, this only works if we have one bound being constant and one bound being a variable. So that works in 3 of these cases. And then we'll talk about what to do in the 4th case in a minute. So for number 1, the derivative with respect to x of the integral of 2 to x of t squared minus 3t plus 1, all we have to do is sub x in, and we'll get x squared minus 3x plus 1. The reason why all we have to do is sub x in is notice we're taking the derivative of the integral. Anytime we have a derivative of the integral, we get the original function back. In number 2, notice that the x is down here. That means that we're taking the integral from x to negative pi. We don't really want to do that, so we want to take the integral from some number to x. So let's flip the negative pi in the x. Now remember from our integral rules that we learned last night, if we flip the top and bottom bounds, that means we have to make it negative. So this is the same thing as dx of negative the integral from negative pi to x of secant squared t dt, and the integral of, or I'm sorry, the derivative of the integral ends up being the function. So what I will end up with here is this function coming back, secant squared x, but don't forget that I had this negative sign out front, so I get negative secant squared x. 3, I have e to the 3t, and we're taking the integral of that from 2 to x squared, and then we're taking the derivative. So what I'm going to do is I'm going to integrate this, and so the integral basically of this would be 1/3 e to the 3t, and then we're subbing in some values for 2 and x squared. Now, one thing that's important to note is that if I'm doing this and I sub in x squared here, so now I will have 1/3 e to the 3x squared. Something that's important to know is since I'm taking the derivative of the integral, I also have to do the chain rule in this problem. So I basically get the function back, but I also have to take the derivative of what I'm subbing in. So I'm subbing in x squared. I have to take the derivative of this as well with the chain rule. So that's important. Now, we would have to do it in these two problems, but what is the derivative of x? It's just 1. So we don't really need to focus on the chain rule in that problem. But if we have anything that isn't just a regular x or something like that, we are going to have to do the chain rule. So if I'm doing the integral here, I get the function back. I sub in x squared where the t was. So I have e to the 3t. I'm sorry, e to the 3x squared. But then I have to multiply by the chain rule, which is the derivative of this, so I get 2x on the outside. So I get 2x e to the 3x squared. Now, why is there not a 1/3 out in front? Well, remember, if I had 1/3 e to the 3x squared, and then I take the derivative of what I got. So if I take the derivative of this, I'm taking this 3x squared, and the 3 comes down, so that kind of gets rid of the 1/3, and then I have to take the derivative of x squared as well. So I end up with this this 2x down there. So it's basically taking the derivative of 1/3 e to the 3x squared. Finally, for number 4, derivative with respect to x of the integral from x to x squared. So notice that x to x squared, that's 2 variables. That's not one constant and one variable. So what we have to do in this case is we kind of have to change what's going on. So we're going to rewrite this as the integral from 0 to x. I'm sorry, I'm going to write that down here so then we kind of see what's going on. So if I have the integral from 0 to x of 5t squared minus 7 dt, and I add that to the integral from x to x squared of 5t squared minus 7 dt, that gives me the integral from 0 to x squared of 5t squared minus 7 dt. So notice that I'm basically just separating the 0 to x squared into 0 to x and x to x squared. That's one of the rules that we learned yesterday. If we have the integral from 0 to x, integral from x to x squared, that's the same thing as saying the integral from 0 to x squared. Now, what the problem has is it has x to x squared. So what I want to do is I want to solve this solve for this thing that's in the blue, and then that'll kind of tell me what I actually have to integrate. So if I subtract this 0 to x to the other side, what I end up with is the integral from 0 to x squared of 5t squared minus 7 dt minus the integral from 0 to x of 5t squared minus 7 dt. I'm going to do all of that and take the derivative with respect to x when I'm done. So what I'm going to do now is I'm going to do some subbing in and then some chain rule action when we have the x squared. So what I have is the derivative of the integral is the function. So I'm just going to take this 5t squared minus 7 and I'm going to sub in x squared. So I have 5x to the 4th minus 7. So notice I just sub x squared in with t squared and I get x to the 4th. Then I have to take the chain rule on x squared. So I get 2x. And then I'm going to subtract the derivative of the integral here, which is just replacing t with x. So I end up with 5x squared minus 7. So I can simplify this. I end up with 10x to the 5th minus 14x minus 5x squared plus 7. I could rewrite it in standard form if I want, but I don't have to. Finally, we're going to take this graph and we're going to do problems 5 through 11. So find h of 3. Notice that in this problem, capital H is the integral from 3 to x of f of t dt. So what I'm going to do is I'm basically finding signed areas. So h of x is finding signed areas. Okay. So if I find h of 3, notice that h of 3 is the integral from 3 to 3 of f of t dt. Okay, so if I'm looking at this, this is the graph of f. Okay, actually, this worksheet has a little bit of an error. So this is actually a graph of f of x. So my worksheet doesn't have that, but yours should be fixed. So we have f is this function, and we're finding this using h, which is the integral of that. So if I look at the integral from 3 to 3, I look at the graph. We have the point 3 comma 0, but it doesn't even matter where the point is. I could have the point at 3 comma 100. Doesn't really matter. So if I'm taking the integral from 3 to 3, I'm basically finding the area under a point. The area under a point is always 0. So h of 3 is 0. Number 6, is h of 12 positive or negative? So what we have to do then is we're basically looking at this graph and we're finding the signed area from 3 to 12. So we're taking the integral from 3 to 12 of f of t dt. And what we're going to do is we're going to look at this. We have a lot of positive area that we're taking, and then we have some negative area, but that negative area is not going to be able to cancel out the positive area that we had up there. So the answer to number 6 is positive. Number 7, on what interval is h increasing? So h is increasing when the integral of this is getting bigger. So the integral of this is going to be getting bigger from 3 all the way until 10. The reason why it works from 3 to 10 is our area keeps getting bigger and bigger and bigger and bigger. And even though the area is kind of getting like these rectangles would be getting smaller, it is increasing our total area from 3 to whatever it is. But then once we get to 10, now our signed area is starting to become negative. So that means it's starting to subtract values from when we're doing this integral. So anything that's below the axis is going to subtract from what we had. So h is increasing from 3 to 10, and it is decreasing from 10 to 15, but it doesn't really ask about that. Oh, yeah, it actually, no, it doesn't ask about that. All right. Oh, number 8 is asking about that. So decreasing is from 10 to 15. All right. On what interval are we concave up and concave down? So if we're looking at concave up and down, what we basically want to do for that is we are looking at, so basically, real quick, let's go back to what we just did. If we have h increasing, that means h prime of x is greater than 0. So h prime, if we take the derivative of the integral, oh crud, the derivative of the integral. Okay, so what is the derivative of the integral? The derivative of the integral is the actual function. So h prime is basically the same thing as f of x. So if we're looking at this, we know that h is increasing wherever it's above the axis, and we know that it's decreasing wherever it's below the axis. So that would be where h prime, which is equal to f of x, is less than 0. So basically we could think about it from an area perspective, but then we can also think about it from the fact that the fundamental theorem of calculus says that h prime is going to be equal to f, so all we have to do is look at where the graph is positive or where the graph is negative. So then that helps us a lot with concave down, because that means h double prime of x has to be greater than 0 for concave up, and h double prime of x has to be less than 0 for concave down. That's the same thing as saying f prime of x is greater than 0 for concave up, or f prime of x is less than 0 for concave down. So if we're looking at this, f prime is just the slope of the graph. So it appears that we are from 3 to 5.853. So from 3 to 5.853, we are increasing. And then we are concave up. And then from 5.853 until 12.813, we are concave down, and then we're concave up again from 12.813 0.813 to the end of the interval, which is at 15. Finally, where does h achieve its maximum value? H achieves its maximum value at x equals 10. It achieves its minimum value at x equals 3. Let's talk about why that is. So it achieves its maximum value when we have accumulated the most positive area that we will have the entire time. That is at 10. And then our possible options for the minimum value are going to be at 3 and 15. And we know that it's at 3 because at 15, we still have not accumulated enough negative, quote unquote, negative area in order to cancel out all the positive area that we got from 3 to 10. So that means that 3 is going to be our minimum value.